We're going to look at this homework assigned at the end of the week, due very soon. I want to make sure that you have solutions available to you. So let's go ahead and begin. We did this problem in class, but I want to rework it just so that we have it complete on the homework. So a planet has twice the mass of Earth and half its radius. So we got to calculate g on that planet. First of all, g on Earth is given by a simple formula. Capital G, mass of the Earth, divided by the radius of the Earth squared. Now what we're going to do is, on our new planet, we're going to simply take some data from Earth and change it around. So we've got the same g as before because that's the universal gravitational constant, but now we're going to double the mass and we're going to divide it by the radius of the object, radius of this new planet squared. So it's got half of Earth's radius. So we'll square that. Now, when we actually simplify this, we're going to end up getting g. And then I can actually pull this 2 out in front times me divided by, now this 1/2 becomes 1/4 when we square it, and that's re squared. And so what's going to end up happening is the 4, when you divide by a fraction that's the same as multiplying by the reciprocal, so we're going to end up getting 8 g mass of the Earth divided by radius of the Earth squared. And to be clear, this number we established is equal to 10 meters per second squared because we're on Earth. So that means this number is also 10. So we're getting a g equal to 80 meters per second squared on that planet. Next, we have a very similar kind of problem where we have a planet that has 3 times Earth mass and twice its radius, and we want to get g on this new planet. To that end, we're going to say that g on this new planet is going to be equal to g times, now it's 3me divided by 2re quantity squared. Being careful with our parentheses, this is going to simplify to 3/4 g me over re squared, which is going to be 3/4 times 10, which ends up being 7.5 meters per second squared. A planet like this, with this kind of acceleration, might actually be the kind of planet that could support Earth-like life, whereas our planet number 1 would not be able to do that. So here we have the acceleration due to gravity of the moon, and we want to determine its mass based on its radius. So we're still going to use the formula g, but this is g of the moon, is going to be capital G times mass of the moon divided by the radius of the moon squared. Plugging in our numbers, we're going to have 1.6 equals. Now we plug in 6.67 times 10 to the negative 11th times the mass of the moon, which is what we're solving for, and that's an 11 right there, divided by 1,738,092, and we'll square that number. Let's be careful when we isolate. So the mass of the moon is going to equal 1.6 times 1,738,092 squared divided by 6.67 times 10 to the negative 11th. When we work that out, we'll end up getting 7.2 times 10 to the 22nd kilograms. Lastly, on number 4, it says that the radius of Earth is this much. We want to know its mass. I'd like to leave you to try to calculate that, but what you should get for the mass, and 5 is a repeat, sorry about that. If you repeat this, the mass of the Earth here, you should get about 6 times 10 to the 24th kilograms. Now questions 6 and 7. I'd actually like us to take a look at those in class together. I'm going to actually do a warm-up question based on one of these two that we'll do in class. So don't worry about solving these explicitly. We're going to talk about these a little bit more in depth in class. So 1 through 4 are really what I'm concerned about. We will continue in the next video.